go ahead and get started here. Welcome everyone to Project Day 2026. This room for most of the day is going to be the Masters of Data Science presentations. So check that you're in the right room. Welcome everyone. This session is going to have 3 talks and we're going to start off with ThirdLine. So let's give them a warm welcome.
Hello everyone, my name is Michelle. I'm part of the capstone team MSDS 26.8 along with Prashant, Eloho and Sanjay. Our project sponsor is ThirdLine and the project we've been working on the last quarters is ThirdLine Access Analyzer. We would like to thank our project coordinator, Dr. Mendeley, our faculty advisor, Dr. Wenjing Yang, and our sponsor liaison, Dr. Sam Gallagher, for the immense support and guidance throughout this project. Before getting the project details, let me introduce you to our sponsor organization, ThirdLine. So who is ThirdLine? ThirdLine is a software company that provides analytics platforms that help government sectors detect financial risk, strengthen internal controls over who can access and use their systems, which in turn can help them reduce the fraud and waste of public funds. So how the system actually works is that it continuously analyzes the Enterprise Resource Planning System data, or ERP, which is basically the operational or financial data to identify unusual patterns, monitor transactions, employee activities, as well as access privileges to identify the potential risks. ThirdLine also ensures that each of their systems aligns with the design of the organization's access policies to help reduce the risk and prevent conflicts. Some of the basic solution requirements that were expected from us in our solution was the access policies such as segregation of duties, which means where no single employee has all the access or control to carry out the critical steps in a sensitive process. For example, an employee can't create an invoice as well as approve it. And to avoid such misuse of this access path, the responsibilities are distributed among different employees. The next is the principle of least privilege, where an employee has just the minimum number of privileges to carry out their duties. And we also have to ensure that we build a system that is scalable and consistent across multiple organizations.
Okay, so to paint a clear picture of what we mean by access management and privilege, think of a time when you've created a shared document for a group project or a shared project. And you probably assign different people within your team different levels of access, such as read only, so that they don't make any changes, edit, so that they're able to make changes, and maybe full control, so that they're able to make changes, download, share, authorize users. That's kind of what we're doing here. And sometimes, as you can imagine, if the organization is large enough, you have hundreds of employees within, it becomes difficult to manage who has what and who has what to do what, right? And so these are some of the issues. We identified 3 core problems. Firstly, manual management of this is error prone. Human mistakes happen all the time. Secondly, lots of permissions are assigned and they work within each other, and it's very easy to just tell which permissions might be causing these violations. And lastly, each organization is structured differently. There is no unified structure, and so it becomes hard to set those solutions. And our main objective is to identify and mitigate high-risk access patterns across organizations.
So we are working with ERP data from different organizations. Each organization has anywhere from 100 to 200 employees, and each employees have up to 20 roles. The data captured 2 important things. One would be the employee attributes, which contains the job titles, the department IDs, and also details about the access, like what kind of access they have and what is the descriptor for that access. And looking at the table, we can see that the access assignments are spread across 4 different frequency tiers, always, usually, sometimes, and rarely. And one number stands out the most. Nearly 9 out of 10 access assignments sit in the rarely tier. And also, procurement and purchasing domain has the largest access assignments, nearly 266 access assignments, and most of it is in the rarely domain with 225, stating that it's the most restricted one. And financial accounting, IT, and system admin are the only 2 domains that span across 4 different tiers. As you can see, an administrator might face challenges while assigning the right mix of access assignments for each employee. So to tackle this problem, we have developed 2 tools.
So we have built 2 different tools. The first one is recommendation tool, which suggests appropriate access, and the second one is anomaly detection tool, which flags high risk access and possible SOD violations. First, let's go with the recommendation tool. Right now, administrator copy access from one employee to another, which overextends access and is very inconsistent. Our goal is to automate that and suggest appropriate access based on the job title. So we split our tool into three different layers. The first one is data preparation. Our data is from multiple different flat files, so we have to merge it and structure it for the next layer, which is semantic pipeline. This is the heart of our tool, which does retrieval and deranking based on the percent similarity. And the third one is to display the recommendations. So here, for now, as in proof of concept, we built a streamlined application where stakeholders can see how exactly the recommendations are.
Before we start any analysis, our data needed some serious cleaning. The job titles were not standardized. The job descriptions varied from organization to organization, and then a director in one team might not look like a director from another team. So to fix these issues, we first normalized the title, and then we ran two kinds of matching. One is keyword based and meaning based matching in parallel, and then we grouped the match results into confidence tiers. And also, we had guard mismatches to capture like conflicting role pairs, like a director being compared to an intern. And the results were strong. As you can see from the chart, almost all the squares are dark blue. 939 out of 1106 employees were matched at high confidence. And then the results were consistent across the different organizations. The medium and low matches represented by the light blue and gold squares are not results of failures. They like reflect genuine naming variation across different organizations. And also the red square has only 4 employees which had no match.
So our tool accepts two different inputs. The first one is job title and the second one is job description. So if, whenever a job description is given, we are using an LLM to classify what exact job title matches with our data set. So once the job title is found, we are going to the first step, which is to interpret the input. Here we are vectorizing the job title. And the second one is retriever, where we are using embedding based percent similarity to find the most similar job titles in our data set. For example, if there are 1,000 job titles in our data set, and here top 500 would be retrieved, and it goes to the third layer, which is re-ranking. What happens here is those 500 job titles passes through an cross encoder, which is a more precise model where each of the job title is compared with the input, and then a score is generated, which gives us strong role similarity. With that role similarity, we are going to aggregate up. So here we are aggregating the access based on the frequencies, which will be explained in a few slides. So first, let's see how exactly we are using LLM to classify the job title. So here we are not using a text classifier because the text classifier fails because the description will be messy and it's hard to understand the context. So we built 3 different agents. The first one is signal extractor. So whenever a job description is given, we are trying to extract seniority, domain, or skills, those types of signals. And the second one is candidate selector. So here we are shortlisting the candidates, like shortlisting the employee titles just based on the description and like based on the natural language. And the third one is title ranker. So based on the output from previous 2 agents, we are using it in the third agent to give a single best job title which matches with the confidence score. So if the confidence score is less than 70%, we are asking the administrator to give more description. So here you can exactly see when an administrator type system analyst, you can see the system analyst and the business analyst, their score is just 0.13% of difference. In that way, their access might be more similar. So if you see access A and access B, for example, access A out of 20 employees, 19 of them have this access, so it comes under always higher. And access B, only 1 out of 20 employees have this, so it comes under rank higher. That's how we are frequency, like we are making the frequency.
Okay, so we're gonna go deeper into the anomaly detection tool. And so for this, we were required to give a pattern-based approach that steps away a little bit from the deterministic current approach that's being used. It still needed to be grounded in probability and interpretable. And so our goal was to build a system that loads in various organizational ERP data and automatically flag users and permissions causing segregation of duties, violation, or least privilege infractions. And so to do this, we followed 4 steps. We first prepared our data. Then we used a tool called Boolean matrix factorization to discover latent permission bundles. And then we fed this into our anomaly pipeline, which we'll get into more detail later on. And then we built an interactive dashboard that IT administrators can use to flag, see flagged employees and make decisions based on that. And so for data preparation, we started off by filtering expansive permissions. We're only interested in permissions that cause or that with broad access rights. Then we put this information into a matrix where each row represented an employee and each column represented the various permissions assigned in that organization. Then we binarized this so that each entry represents whether an employee has or does not have a permission. 0 meaning it doesn't have, and 1 meaning they do have. And lastly, we removed baseline permissions. These were permissions that we saw being held by more than 80% of our population. So this is basically what we've created at this point. And our goal is to be able to highlight, for example, employee 3 that is given permissions that they do not need. And so to do this, we had to first learn how permissions were being assigned. And so the Boolean matrix factorization splits that first matrix into 2 smaller matrices, the one telling us about how permissions are being bundled together. So for example, you can see finance bundle with various permissions and admin bundles with various permissions. And then the other matrix tells us more about what permissions each employee has or what bundles make up an employee's permission. And so, for example, Sarah has her permissions within the finance bundle, and David has his permissions split between 2 bundles, finance and procurement. And so we had to test this to make sure that we're actually learning something right. And so we did this by masking different percentages of our data to see if we can retrieve these bundles correctly. And as you can see, even with up to 30% of our data being masked, we're still able to achieve an accuracy of 74%. So we could trust this. So we moved forward. And we fed this into our anomaly detection pipeline. So we start off with our bundles that we discovered, and then we have an expected score where we reconstruct back those 2 matrices together. And so basically our risk score logic follows this, where a low expectancy of the permission added with a permission that just happens to be high risk flags that employee. And that's basically what we did here. And so to give you a snapshot of what's going on, as you can see, this is from one organization that has up to 291 employees, and we were able to flag 33 employees for review. This gives us a 91% reduction in scope review. You can imagine how long it would have taken to go through each employee within this organization to find if there are any violations. So we were able to zoom it down to just 33 employees, making this process faster.
So putting it all together, 2 different tools, and we have 2 sets of key findings. Recommendation tool, as you can see, the financial access recommendations spanned across every tier, consistently from 38% to 56%. And then the procurement was the most restricted access recommended. Around 42% of the recommended access fell under the RAP tier. And for us, for the anomaly detection tool, the highest exposure ranged from 12% to 38%, 68% across different organizations. And 380 employees were flagged with unusual access, generating 4,760 actionable flags for review.
Some of the limitations we faced was that we didn't have labeled output to validate the system completely. The job titles were inconsistent across many organizations, which made it difficult for the recommendation system to retrieve comparable employees. The data was so sparse that some of the roles had very few comparable employees, which reduced the potential of the recommendation patterns. And different organizations had different roles and procedures, which made it difficult for us to build a global anomaly detection tool. In conclusion, our 2 data-driven tools, they transform ERP access governance from a more manual review to a more consistent and scalable approach. And our recommendation tool uses semantic job titles. The anomaly detection tool uses a more learned access bundles. And together, these 2 tools provide interpretable insights, which also support the SOD and the least privilege review. Our system also provides a flexible foundation, which can be extended further using labeled feedback as well as organization-specific SOD tools in the future. Thank you. We'll be happy to hear your questions.
can raise your hand for questions. I'll bring them right to you so that people online can hear. Okay, I'll kick off one question. I'm curious, with your LLM based semantic match, what LLMs did you use and how did you vet them?
So for now, we've used it's in just to see how exactly the LLM is being classified. It's the first version, so we've used Claude Haiku for this. And what's your exact question?
How did you implement it and how did you also check that they were working correctly?
So it's completely based on retrieval. So it's nothing with respect to generating. We are just calculating and trying to get out signals based on it. So we are not having any specific hallucinations here, and we've set the temperatures to 0. So our LLM will be more precise.
In the first step, you mentioned for the signal extractor, you're extracting seniority domain skills. So did you try it with the traditional named entity recognition approaches instead of LLM?
Yes, if you see our first data preparation step, we try to use that. But why we exactly use this is because our description is very sparse, and the descriptions can be very vague as well when an administrator gives. So at that time, trying to get exact key signals from just with the word, it's quite hard. That's why we try to get specific words from LLM, and then we again use get signals.
Okay, I have one more question for you. When you did your matrix factorization, can you talk a little bit more about why you chose Boolean matrix factorization versus other methods?
So in our initial approach, we had tried our typical clustering, but our data was too sparse and wasn't able to pick up any like device signals. Some job descriptions or permission were being left out. And so we needed a technique that handled sparse data well, and that's where Boolean matrix factorization does great that.
Okay, any last questions?
What would your instruction be to the end user? They use your factorization and get some anomalies. What would you say is their next step for checking if they're getting false positives on anomalies or true like outlier questions?
That's a good question. I think that's something that we're still working on, but I'd say as of right now, our next step would be to also try to run this on train like specific kind of data, like a model data that would give us the ideal bundling and the ideal situation, so that when we run this, we have stronger signals through our bundles.
Okay, let's thank our speakers. We have a couple of minutes until our next talk gets started, so feel free to go get a snack and then come back 1:05.
Oh, yes. Yeah, hopefully they'll I swear it is. You don't think I'd see good action. And that's just saying. Yeah. Yeah, I think so. Questions on this. Okay. Permissional set versus one. What's the amount? You can get a good. Yeah. How do you feel this one? How do you all feel? Okay. Yeah. You're trying to you have to go take someone to college. Well, please explain some. First part. Ways.
Okay, let's welcome our second team from Tacoma Power.
Good afternoon, everyone. Thank you all for being here today. We are Team MSDS 26.7 and we are excited to present our work, Transmission and Distribution Poles Inspection Program Analysis. Our sponsor is Tacoma Power. I'm Alexa. My teammates are Stefan, Moinuddin, and Becky. So we walk by these electrical poles every day, but have you ever wondered what goes behind the scenes to properly maintain them just so we can get uninterrupted supply of electricity? Here comes our sponsor, Tacoma Power. So, Tacoma Power is an electric utility company that manages more than 50,000 electrical poles, serving more than 200,000 customers in the greater Tacoma area. So, to manage their vast infrastructure, they conduct a program called Test and Treat, in which they check the poles for any damage and decay, and they also do the required treatments. And these are usually done by the third-party auditors. So they use standard procedures like visually inspecting the pole, using a hammer to do sounding and boring. And based upon those results, these poles can be treated, monitored, or even replaced.
So every year, Tacoma Power runs this program. They accumulate inspection data. And since they've been running it for over 10 years so far, there has been a large accumulation of this data. So then the question becomes, what kind of insights or information can we extract from it that would lead to the highest operational business value for Tacoma Power? And to decide this, we looked to the data and we also collaborated with their team. We concluded that the highest value for Tacoma Power would be to understand the main causes leading to the electrical pole replacements, because knowing this would allow them to effectively use their resources to increase the longevity of their pole infrastructure, which will therefore in turn reduce overall costs associated with replacements. So we want to address this problem fully. We want to analyze it from 3 different levels. We first looked at the whole region level, which is just the overall distribution of the main causes leading to the replacement of these poles. We then wanted to look at sub-region level differences, because we want to understand if there are any nuances or details associated with differences between smaller subregions. For example, you can imagine that poles closer to water would likely have more decay, whereas poles closer to wooded areas might have more bird or insect damage. So we want to highlight those types of differences. But we then also look at yearly level differences, because we want to understand if there are any time-based patterns in the data. And what I mean by this is, if you can imagine that rot on the outside of poles is increasing year over year, we want to be able to let them know about this so that they can include preventative types of treatments. So our solution and our method to solving this problem was to create a 10-stage, fully automated and reusable machine learning and analytics pipeline, which we created in 4 different phases. And the best way to think about each phase is that they answer a very specific problem. So the first problem is that with phase 1 is in our ingestion phase, it answers where are we going to get the data from. The second phase, which is our data preparation phase, it answers how we're going to get that data ready for modeling. And then our third phase, analytics, answers how we can extract those insights from the data. And then lastly, our delivery phase answers how we're going to report those results to Tacoma Power. So now we can dive into each phase to see a little bit more detail of what's happening.
Let's start with ingestion. A SharePoint folder what is for any new data files coming into it and automatically kicks off the pipeline. We then use a custom parser which pulls out all the columns we need and combines them into a single data file. And the result, without any physical work, we end up with one single data set that could be used. And now comes the cleaning. Every inspector inspects enters a value in their own way. This results in many missing values or placeholder values. So we define a shared schema which maps all these inconsistent values to our meaningful values. And we end up with one single clean data set for 10 plus years of data which could be used for analytics. Apart from all the data points we had, most of the information was present in free text as inspector comments. So we use an LLM to classify all those comments into specific categories. We then use regex and spacing to categorize all the comments which we had into those categories. Doing this, we were able to recover most of the values which are present in comments and not in the data points. And the result of this is one clean data set with all features from the comments. And since we were able to extract most information from comments, we turned them into features for a data set. And with some research, we were able to understand the black box variables which we had in our data. And breaking them down into 100 plus variables for our data. And we end up with a feature-rich clean data set which could handle off analytics.
Okay, so now that we have a clean data set with an enriched set of features, our next step is to use machine learning not for prediction but for interpretability, where it helps us to understand what's causing the pole failures or pole replacements. So to this, we designed our modeling strategy around the goal of maximizing the recall, where the model have to capture as many rejected poles as possible so that we can effectively interpret using the model learnings. So to make it realistic, we trained this data using inspection data from 2013 to 2023, validated on 2024 and tested on 2025, respecting the time series nature and preventing the data leakage. We finally evaluated using different machine learning models, starting with logistic regression and then tree-based models. So after evaluating our different models, we finally chose XGBoost as our final model due to various reasons. The first one being its capability of handling nonlinear interactions well, and then its robustness on tabular data with missing values and data imbalance. And most importantly, this particular model captures a broader set of rejection poles, as we can see in the confusion matrix to the right, where out of 956 rejected poles in the test data set, the model missed only 8. So this made the model for explainability and which are more reliable. So this is where it gets really interesting. Now we have well-performed model. So we then used SHAP technique, which is Shapley additive explanations, that helps us to understand what model actually learned. So think of a SHAP as a way to ask the model for each pole that was flagged as rejected, which feature made that decision, pushed the decision towards rejection, and by how much. So here, this plot is mainly for one specific pole that helps us to answer why this pole needs replacement. And the SHAP values for each feature indicates or measures how much the feature changed the model predictions from compared to average prediction. So for this specific pole, external decay was one of the biggest contributor for the pole replacement, followed by woodpecker damage, internal decay. But whereas the pole condition for this pole actually reduced the risk of rejection,
this was due to the top of the pole condition is really good, but the overall combination of the decay factors outweighed this pole top condition. So overall, we looked at one specific pole, but SHAP also provides a global view by aggregating all the individual explanations, and this will be further discussed in the results.
So up until now, we've seen how we have ingested our data, cleaned and standardized to form a single data set, upon which we did some analysis to understand why these poles are failing. Now, in the last phase, we have published all this data into Snowflake, and Snowflake saves this data in the form of relational tables. And it also has a reporting tool called Streamlit, where we've built some interactive dashboards that our sponsors can actually use. Now, let's take a look into how we answered our initial questions. So this is the dashboard that we have built. Now let's talk about it briefly. This shows the overall infrastructure view of Tacoma Power. At the top, you can see the total number of poles that are inspected. There is also a geomap that would enable our sponsors to look at the exact location of the pole. Next to it is a line chart that would show the rejection rate over the years. And we can say that post 2020, there is quite a bit fluctuation in the rejection rate. There is also a horizontal bar chart that tells us the reasons why these poles are failing, which I'll talk about in a minute. Now, next to that is a line chart that shows the trends of these features over the years. So this is the bar chart that shows why these poles need replacement, and the strongest contributor is pole top condition that accounts for more than 40%. That is followed by woodpecker damage and the age of the pole, and the next two reasons account for the decay reasons.
So, coming from the sub-region level, we compared two regions which were close to each other. As you can see, the pole top condition is a leading factor in both of them, and it has been a far more factor in region two. Apart from these, the pole replacement are driven by most other factors like pole age, shell thickness, and pole integrity. The key takeaway from this was the two regions might have similar replacement rate, but the reasons might differ a lot. So our modeling helps Tacoma Power understand those regions so that they could take measures accordingly, not have one solution for everything.
Okay, so now we have identified the key rejection drivers for the pole replacement. Let's look at how these rejection drivers vary across 13 years of inspection. So in this panel, we have each plot represents the feature and its contribution over 13 years. So first we have pole top condition. So over the years, the condition of the pole top has a significant impact on the pole replacement. So this tells us that the pole top degradation has increasingly critical concern for the replacement across entire fleet. And then we have decay factors, shell thickness, and shell draw depth, where we can see the initial spike in the early inspection cycles, but over the time, the effect of these decay factors has really declined. So this tells that the test and treat program by Tacoma Power has been progressively effective in treating the decay-related factors. But one important trend to notice is the pole age, where we can see in the initial inspection cycle, the effect is really negligible, but over the years, it's been there has been an inclination. So the age or age-related structural degradation has becoming a growing driver for rejection. So unlike decay factors like shell thickness, shell draw depth, which can be treated, pole age is something that's irreversible. So this trend really has a real implication on the replacement program going forward.
So in summary, our original goal was to understand the main causes leading to the replacement of these electric poles, because we firmly believe that this would have the highest value for Tacoma Power. And our key finding across all levels of analysis was that pole top condition was by far the dominant cause because it accounted for 43% of all pole replacements. So therefore, our recommendation to Tacoma Power is to focus the prevention and treatment efforts on pole top preservation because it has the greatest value for them as a business. Now, I can draw an example for the business impact. Now, let's just assume that they treated the pole tops and in the following year they had a 5% reduction in their pole top related rejections. And on average, they replace 840 poles each year. 5% of 840 is 42 poles. And we multiply that by the cost of replacing a pole, which is $10,000. This leads to a potential annual savings of $420,000 simply by reducing the pole top or increasing pole top preservation so that there's a 5% reduction in those replacements. And I wanted to highlight pole top condition above all the others because it stands at 43% of all the causes across all the causes for replacement. And so by reducing it by 5% to 38%, it's it's much more feasible than if we were going to reduce, let's say, a cause that was at 10%. And so it is this line of reasoning that allows us to firmly conclude that the highest business value for Tacoma Power would be to prioritize pole top preservation because it is by far the main driver leading to pole replacement.
So at the end, we would like to thank our faculty advisor, Dr. READEASE, our sponsor representative, Deja Morrison, Dr. Mendeble, Tacoma Power Team, and the Project Center for constantly guiding us. Thank you all for listening. If you have any questions, we would love to answer, or if you'd like to discuss anything, we'd like to talk about it more. Thank you.
So for the pole top preservation efforts that you were talking about right at the end, presumably there's some amount of cost associated with that. How do the costs differ for the different preservation efforts, like pole top versus woodpecker damage versus whatever else? Is that something like are there differences that are substantial enough there that might influence some of the decision of what to prioritize as well?
Yes, definitely. So the issue with the pole tops is because of the inaccessibility to them, it's requiring much more levels of equipment, and then it's also more risk involved with treating them. And then you're closer to the electrical lines at the top. So that's like one of the main reasons why the efforts are still not really clearly decided upon for choosing like the types of treatments or anything, because there's still not a clear answer to this question. So the cost that would have to be included in that is like research costs and to actually decide what is the most effective way to be able to treat those. Versus like decay at the ground line, for example, when it's just around the pole at the base, it's very easy to treat because they have this paste that they rub around it that prevents the decay. But then it's just the accessibility of that is so much more easier than being able to either bring up a ladder or as part of their trucks also have like a kind of like an automatic thing that brings them up. I don't know exactly what it's called, but however, there's the risks associated with it is much greater.
Other questions? Okay, I have one question. I know that your data kind of management and standardization was a challenging part of the process. Can you talk a little bit about the decisions that you made in there, and specifically how might you have introduced errors and how might that affect your final model?
Okay, so the main challenge for us is to know what certain features meant. So we actually had lots of talks with our sponsor and have been very supportive. Also talked about each of the data feature with the 4 people who are actually inspecting about it. So mainly we made sure every feature is being standardized, as it is being various inspectors have different ways of putting in the values. So it took us a lot of time to standardize it. We had to talk about it, and we also read multiple documents to understand the levels, like at what value is the thickness leading to the decay of it. So that is something very challenging. So thanks to all the documents our sponsors have provided, we have actually gone through everything and we discussed it. So the limitations could be that in the future, we do not know. There are some of the reasons like fire damage, which we do not have much data. So that could be one of the limitations.
Okay, let's thank our team one last time.
How was that?
I think maybe you're, yeah.
Okay, so for our last talk of the session, we're going to hear from Puget Energy, so let's give them a welcome. Great. Hello, we are Team MSDS 26.5, Dana, Nicole, Ellie, Naveen. We are identifying electric vehicle charging gaps for our sponsor, Puget Sound Energy. Now, Puget Sound, is it, oh, is this? All right, I'll give you a point, Naveen. All right, great. So, Puget Sound Energy is the largest electric utility provider in the state with over 1.2 million electric customers across 8 counties. And as the name suggests, that electric service area includes most of the Puget Sound with some exceptions like Tacoma. However, it extends even further into central Washington. Now, Puget Sound Energy is considered a monopoly, which means they are regulated by the Washington State Utilities and Transportation Commission. What this really means is that their profits are capped by the state, and so if they want to make any changes in rates or they want to do future investments, they need to justify this and get state approval. Next slide. Thank you. And so PSE has long-term energy goals of supporting the transition to clean energy, and that includes reducing carbon emissions. And one big way that can be done is if more drivers switch from gas-fueled cars to EVs. And so PSE can directly facilitate this change by providing public chargers for these drivers. There are other companies that offer public charging, but they're really just focused on placing chargers where they will immediately get that money back. PSE instead recognizes that if they focus on equitability across their whole service area, they'll help more people transition to EVs, which will support their goals in the long run. Next slide. And so why talk about EVs? Well, EV ownership is on the rise. In Washington State, we had over 200,000 registered in 2024. However, despite this predicted increase, one big reason people give for why they don't swap to EVs is charging anxiety, also called range anxiety. The fear that if you're out with your car and you need to refuel and there's no charger, it dies and you're stranded. PSE recognizes that these are the drivers they can specifically help feel comfortable switching to EVs if they can provide that robust charging network to alleviate this concern. And when we talk about charging, we should explain the 2 types we're really focusing on. First off, you have level 2 charging, which will charge a car in a matter of hours. The use case for this is destination charging, where you reach your destination, you will be there for multiple hours, so your car can charge the whole time, ready to go when you're ready to go. The other type is level 3 charging, aka DC fast charging. This type will charge your car considerably in just a matter of minutes. The use case for this is what we call corridor charging, which think is just akin to your typical gas station experience of you're driving down the road, if you need to refuel, you just want to stop for a few minutes, get right back to going. And so while these are the 2 types that should be available,
If they're actually available to you is a different question, because as you see where they're located, it's not a lot. They're really just in a couple super dense urban areas, and what looks like a relatively high number is here as shown at the max 6 chargers per square mile. So it really, as a whole, this just means there are a lot of drivers who are left out of the EV charging network.
These challenges lead to an important question for PSE. Where should they install their new public EV chargers? Well, our project aims to answer this question by building a spatial decision framework model that will tell PSE where to put their new chargers. Our key deliverable is to identify the gap where EV chargers currently exist and where they're most needed. PSE also recognizes that the barrier to get more people to actually own EVs is the lack of public charging infrastructure. So we want our model to prioritize equitability and ensure that chargers are accessible across diverse communities. One main requirement is that our model needs to be flexible. This means that PSE needs to be able to change the weights or priorities of different inputs into our model. This is mostly important to distinguish between trends, like different use cases such as corridor or destination charging, and also different charger types, like level 2 and DC fast chargers. Our model also has to identify a specific enough geographical level to ensure that PSE can make data-driven and smart decisions when placing their chargers. So we will analyze our model at a census tract level. Census tracts are smaller geographic areas than counties, and they're defined with communities of similar population sizes as well as demographic characteristics. A census tract level model will give us localized charging need, but we will also take our project one step further and do a road level analysis. This analysis will give suggestions to PSE for exact charger placements in high priority areas. Lastly, we will do a sensitivity analysis that'll test how our results can change based on different weightings or inputs to ensure that our model suggestions are consistent and confident across all tracks. So to model our EV charger need, we split up our features into 3 main groups. The first main group being current demand, which includes features like traffic intensity, trips count, and average dwell time. Together, these features reflect how EVs travel through certain areas. The number of EVs that are currently registered per census tract are also part of current demand. Our next group is equitability, which ensures that our model considers underserved areas and ensures that PSE can place chargers where they have high impact. Highly impacted communities, or HIC, is a Washington state-defined term that reflects health and economic disparities. While vulnerable populations are values given to us by PSE, and they reflect socioeconomic disparities. Our last group is future growth, and here we've calculated the potential for EV adoption by taking the total number of people in a census tract and subtracting the number of EVs in that area. This will show us areas where EV adoption is low and where there's potential to grow. To calculate our gap, we first have to scale our need. PSE has given us projections for how many chargers they want to implement to reach their goal by 2030. So we will scale our need to match their numbers, and then we will subtract the number of current chargers that exist per census tract to get our gap. Overall, our gap will represent the number of chargers that PSE needs to implement in each census tract every year to reach their goal by 2030. Here's an example of what our model output would look like and how PSE might use our results. Here you can see the census tracts that surround the Puget Sound region, where darker green census tracts represent higher gaps. We can see that tracts near Seattle and Bellevue appear white, meaning that these areas are overserved and likely not a focus for PSE. However, the tracts near Renton and Kent appear much darker green, showing higher gaps and can be areas of focus when PSE is implementing chargers.
For some higher level, simpler and more interpretable results, we aggregated our tract level results to the county level. So this chart shows just the total gap sums for both levels of charging by county. And we see in this chart that the larger counties that overlap more with PSE's service area tend to dominate. But one interesting thing from this chart is that Kitsap County has a large proportion of level 3 need than we might expect given its overall gap score. This chart shows the distributions of tract gap score for level 2 chargers ordered by county. Values less than 0 represent overserved tracts, and a wider distribution means a more inconsistent gap score across the county. The counties with the highest median gap scores are shown at the top of this chart. So one of the things that emerges from this chart is that Pierce County shows up as one of the most consistently high gap counties within PSC's service region. This means that there's a lot of very high gap tracts in the areas, not within Tacoma, but outside of Tacoma, parts of Puyallup and these areas show high gaps. Whatcom and Thurston County are smaller overall, but they also show consistently pretty high gap scores near Bellingham and Olympia. King County has a very high median gap score, but it has a wider distribution than any other county, so it has more of an inconsistent impact across King County. There are areas mostly in southern King County that show very high gap scores. Renton, Federal Way areas, and Kent areas all show high gap scores, but other areas are overserved. And Kittitas County also shows some moderately overserved tracts. This is the same chart as before, but now we've included some extremely overserved outlier tracts. They're shown as red dots to the left side of the chart with very negative gap scores. So while King County isn't the only county that has overserved tracts, it has the most examples and the most extreme examples of overserved tracts. This means that there are a number of areas in King County that are already sufficiently targeted by other charging providers. So one of the things when considering evaluating our gap model, it's based on many assumptions taken largely from existing literature, but there's no way to directly evaluate its accuracy before investment decisions have already been made. So it's very important to understand the sensitivity of our model outputs. So there's two key questions we considered here. The first one is how sensitive is our model output to small variations in the input data. So to understand this, we've used a noise injection procedure and over many iterations evaluated how the rankings of our model changed. One of the key findings from this is that the most stable tracts in terms of how their rankings changed tended to have a higher gap score overall than less stable tracts. This is a generally good finding because we would hope to be able to find some areas that have consistently high impact so that we can make more confident investment decisions. The second thing we asked ourselves and looked into was how sensitive are our model outputs to changes in the input priorities. So these would be the weighting choices assigned to the inputs to our need calculation mentioned on a previous slide. So we assessed this with global sensitivity methods. We use both Pond statistics and Shapley effects. Shapley effects look at the influence of each model input weight on the output variance, while Pond statistics look at the influence on the output cumulative distribution. This chart shows the relative influences of each of the model input weights on the output. So on the left side, on the y-axis, each of these factors corresponds to one of the individual measures or one of the groups that goes into our need calculation. We see from this chart that the most important weights to pay attention to when making decisions are the equitability group weight and the EV adoption potential. So EV adoption potential is the only indicator within its group, so that might be considered the most important weight to pay attention to overall.
So here the road level analysis. So in census tract, it identifies the high charges needed areas, but for PSA it is too broad in which area charges are going to be planned. So in the road level analysis, it's inside the census tracts. It's individual road segments review the first where the charges are for the future planning. So for the road segment reviewing, so we consider the three main factors. One is the travel activity. So where the driver's movement is stronger and charger coverage. So here in some of the areas they have existing chargers. So by adding the chargers, it maybe reduce the access gap at the local feed where the roads are nearby the destinations and highways and commercial areas and other destination areas. So it's easy to make the score for road level analysis. So here is the map final road level. So in this map, you can see the corridor score and destination score. And for destination, so some of all here in the road segment, not only for corridor and destination, some of there are score for both the destination and corridor. That's you can see the violet color. In the Renton, it is the mixed patterns because Renton is local destination and regional corridors. So you can see the multiple road segments, what are the charges they needed. And the value, so in value, they already had the existing charges. So it is also a major activity area. So they are showing the gray color, which is like low priority, low monitor area. And ISAC is I-90, so it is a corridor based. Yeah. So in the chart summarizes the estimated cost needed by county by 2030. So in this plot, answer the questions in which county road segment should be reviewed first, and the scale of investment in the counties. So right now, these models use the PSC where the charges is going to be installed, but charges demand changes by the day of the time. So for example, for the employers, so they're gonna stay for several hours during work hours and travel activities. So where the drivers are gonna stay for longer hours on in the corridors. So this by adding the time-based travel behavior gives the PSC not only the way that charger stations are going to be installed and what type of and how long the driver are going to be used. Yeah, and this model gives the PSC for future charger installation and infrastructure investment across the Washington. So we want to thank our sponsor, Graham, and our faculty advisor, Dr. Slaughter, and Mendable and Seattle Project Center for supporting our capstone projects. Thank you.
That's good.
Hey, yeah, I apparently am saving my question for the presentation when you could answer them, in the months before. So curious, how or with the gap score that you predicted, both or at the road segment level, did you look at all into how that correlates or relates to the equity metrics like the highly impacted communities and the vulnerable populations? I ask because a lot of times you find that those infrastructure is built with systemic disadvantages built into it. So when we start using infrastructure as the way of allocating need, you're baking in the systemic disadvantages that are already built in. So I'm curious, did you look at the relationship between the road level gap metric and the equity data pieces?
No, I didn't.
All right.
Other questions? Okay, I have a question for you, and I'll give you my back so you can answer to it. So what were your main limitations that you faced in terms of both the data availability and then also things that you needed to learn on your own that you found very challenging or hard to find resources?
I can speak to that a little bit, and then maybe other people can chime in on the team if they'd like to. So in terms of data availability, there is not, the main thing is that there's not a lot of current, well, there's a couple of main things actually. On the one hand, as far as current charging infrastructure, there's still not a lot of it. And there's not a lot of like kind of longitudinal data to see like how it's been developing and how that, relates to different factors in a way that we could really confidently predict based on other factors in places that it doesn't already exist, like is it going to get installed soon by a different company. Another issue is that a lot of our different data sets are geographical in nature and they're available at different geography levels. So there's a couple of key challenges there. On the one hand, trying to make the most granular analysis we can be difficult when some of the data maybe is only available at a census tract level and no more granular than that. Another issue is that some of the data might be available in 2020 census tract geographies, and other data is available in 2010 census tract geographies. So there's a lot of kind of crosswalking of those values involved, and that results in some estimation error. I think those are the two main data.
And I guess it was nice that a lot of it was publicly available data, but that does kind of come with the risk though of like, people can say like, yeah, this is at the census block level, and then you go through and you're like, this actually isn't. So that is, even though it's publicly available from like state agencies, you still do need to double check it.
One last question.
I'm just curious if you're able to, on your demand side, understand like how many stations are like privately developed. You know, if I have a car and I have one in my garage versus like is PSC able to show like here are people whose charging bills spiked at the night overnight to help with that type of demand?
Graham has not told us if they're doing that sort of surveillance, but for the majority though of people, especially as you consider like equity, like being able to install a charger in your home requires like that you own your home and can make changes to it, and that the electrical wiring within it can handle it. And so for a lot of people, like that's just not the situation they live in. And so, I mean, obviously that is something to consider if it's there, but I think for a lot of people, and especially when we consider like equity, that's not a huge option for them. So
a lot of that data is also, it's available like in the permits data, which would require a lot more time than we had at the end of the project to kind of come through and do a lot of scraping of the permits data and figure out who was actually installed private chargers. So some of the limitations.
Okay, let's thank our speakers one last time. So we have a short break and we'll be returning here. We're gonna go ahead and get started again. So this session, we're going to have 2 MSDS talks, and then we're gonna have a computer science talk in the third slot. So let's welcome our first MSDS team, which is from Mercer Island School District.
Great. Well, good afternoon, everyone. We are Team MSDS 26.4, and our capstone topic is titled Equitable and Inclusive Learning, Aligning Values to Outcomes in the Mercer Island School District. Our team members are Akash Krishna, Art Anamstride, Jesse Lloyd, and myself, Mark Gaza. Our faculty advisor is Dr. Yang, and our sponsor organization is Mercer Island School District. Today, we'll be presenting how we use student attendance demographic data to help Mercer Island better understand outcomes patterns and help identify areas where targeted support may be most useful. To begin, the motivation behind our project is that Mercer Island performs academically well overall. That is one of the strengths of the district. However, one challenge when looking only at district-wide averages is that they can hide differences in student outcomes, growth, and opportunities. A district may look very successful overall while still having a group of students who are not experiencing the same outcomes or the same level of growth. So the key question guiding this project was, do all student groups benefit equally? This doesn't mean that we came with the assumption that disparities existed everywhere. Instead, our goal was to look beneath the averages and let the data tell us which pattern needed to be further monitored or they needed further support. Our goal project was to turn student insights into actionable insights for Mercer Island. We focused on 3 main objectives. We wanted to analyze student outcomes using academic records, attendance, demographics, so that we can validate performance across student groups rather than just looking at the district averages. Second, we wanted to evaluate growth over time. This was important for us because achievement alone does not tell the full story. A student may not yet be at a grade level, but they could be making strong progress. On the other hand, a group of students may look like they're doing really well, but their growth could be slow. Third, we wanted to build a usable dashboard. The goal was just not to complete a one-time analysis, but to generate visuals that Mercer Island can continue to use in the future. This slide shows the analytical workflow that we followed throughout our project. We started with data collection, which included assessment scores like SBAC, iReady. We also had attendance and demographic data as well as academic records. We then moved into data cleaning. This was an important part of a major part of our project because data sets came from different sources and they needed to be standardized before we could do comparison across students. Once the data was cleaned, we conducted statistical analysis to compare outcomes and growth patterns. This helped us identify where there were, meaningful differences across students. Once the data was cleaned, we used machine learning to better understand which factors were associated with outcomes like GPA or academic risk. So our goal was to treat these models as interpretive tools, not just as prediction tools, because the goal was to find patterns that Mercer could use to monitor students in the future. Finally, we translated these results into a dashboard with the goal that it would make the dashboard more accessible and easier to monitor these patterns over time. So now that we've gone through the project of motivation, goals, and the analytical workflow, in the next section, we'll go over what we found in the data.
So let's start at an area where we might expect some inequality, that the relative placement. What is relative placement? If I take the iReady state assessment standardized test in 9th grade and I get a score that places me at the 8th grade level, that means I'm one level below. So now that we have these groups, what are we measuring? We're measuring what proportion of these groups have successfully grown at least one grade level between the fall testing period and the spring testing period. That's one academic year. And some good news. Looks like the district's responding well to the groups, especially the two groups that are doing the worst off, 3 levels below and 2 levels below. Looks like a huge proportion of them are successfully growing at least one grade level in this period. So this is very good news for us. But let's look forward a little bit into the future, maybe 3 months into the future, at the fall to fall testing period. This is 1 calendar year. And it seems to us that for our 2 groups that seem to be doing the worst off there, all of their peers have caught up. Even worse, all of their peers have exceeded them in the proportion. What could have happened? Like a summer pass. What could have been the cause for this? So we thought that, well, perhaps students that are behind might have fewer financial resources, maybe less summer programs or academic enrichment. So let's actually take a brief look at the low-income, non-low-income comparisons. And it seems like we don't have too much evidence to back this up. In fact, the groups are almost the same. But some additional good news here. We see that the district is actually, for low-income students, for the English test, they are surpassing their non-low-income counterparts by about 5%. This seems to hint at a very, very strong English language learner program. But now that we've exhausted kind of these 2 groups in terms of insights, let's talk about something like attendance.
Thank you, Jose. Using TDS analysis, we found several significant difference student performance in across student groups. First, we look at how attendance impacts student groups. Attendance was one of the most strongest predictor of student academic success. Look at the left plot. You can see that students with higher absence rates had lower GPAs. For example, students with 20% or more absence had lower GPAs than better attendance students. Look at the right graphs. You can see that the students with chronic absenteeism students were 13 times more likely to have GPA below 2.0. This results suggest that attendance is a strong early warning signal in our school district. Next, we examined income-related difference in student performance. The left graph shows low-income students had lower GPAs than lower income students. A gap of about 0.33 GPA points. The right top shows that gap persists across most grade levels. You can see that largest difference in grade 7th and 11th. These results suggest income-related achievement gap present and remain, and we continue to monitoring. Third, we examined academic outcomes for English learning students. You can see this plot shows us how current English learning students had lower GPA than non-English learning students. A gap of about 0.28 GPA points. This suggests that achievement gaps associated with English learner status still remain and should continue to be attention.
So now we're going to move on to the machine learning. Why are we using machine learning? Are we trying to predict the future? No, the future belongs to the students. What we're interested in now is seeing which factors that the machine really likes, and we'll use those, okay? So we're gonna take as many features as we have, take it all. We're going to feed it into our machine learning model, and it's going to spit out one of two things. Maybe it'll spit out a number, maybe it'll try to predict the GPA, maybe it'll try to predict the status, like at risk, not at risk. Once we test the model and see if it's pretty good, we'll look at the most important variables, the ones that carry the most weight, and then maybe we'll get to some gems. But let's check to see if our models are good in the first place. What we're measuring with a couple of these models is the R-squared score. The R-squared score is another way of saying how much of the target variable, GPA, is being explained by the variables we put in. Now, we have, if you see here, we have 60% and 62%. Okay, that's a pretty bad grade. But in terms of R-squared score, it's pretty good. It gets around the gold standard of the social sciences, around 0.60%. Now let's look at these variables, so, okay? What we're measuring with these variables, it's going to be the SHAP value. The SHAP value, what does it mean? It's another way of saying kind of the relevance of the variable, how much work the variable puts in to explain the target variable, GPA. So if we look at a couple of the top predicting variables, to no one's surprise, if you do pretty well on a standardized test, you're gonna have a pretty good grade. I'm not too shocked about that. We do see attendance here playing a pretty important role, but let's look at some more interesting variables, okay? So if we see here, these the bottom two bars represent two statuses you can have, chronically absent and low income. And we can see we have kind of a prediction of just how much your GPA would be affected if you are missing more than 10% of your classes and if you're a low income student. So that's what some of the work that we've done trying to predict this numerical GPA. Let's move on to the classification model though.
Now I'm going to introduce our second machine learning model, academic risk classification model. Our purpose of this model is to identify students who may be at risk before poor academic outcomes occur. We define it academic risk, define it as having a GPA 2.0. In this slide, present the most two best performing classification models, which is random forest and tuned random forest. You can see that tuned random forest model demonstrated strong performance. It can say our model was effective at identifying students who may need academic risk. This suggests our SHAP analysis shows most important predictors of students' academic risk. You can see that special education predictor was most strongest predictor, followed by income, gender, and English learning status. This results help schools to identify students group may benefit from additional support to improve academic outcomes. Akash?
Right. Awesome. So we want to try and consolidate a lot of this information so that the school is able to take it and use it in future years. So what we did was we created a sort of interactive dashboard where the objective is for the school to be able to track some of the metrics we talked about here today and also be able to feed in their own data for future years really easily so they can continue to track these stats. If this is something you're interested in hearing more about, we have a poster upstairs and we're demoing this, so feel free to check that out. It also gives parents and guardian figures something to be able to hold the district accountable if it's publicly available. So, let's talk about some of the recommended areas for action we can come up with based on what we talked about here today so far. Something we saw was that certain students over the spring to next fall kind of gap, they were starting to fall behind a little bit. We suggest continuing academic support beyond spring for these people in some way, ideally something over the summer. Something else we noticed was that beyond that like 10% cutoff on attendance, and it was a very strict cutoff at around 10%, academic GPA would kind of just fall off a cliff. And we recommend the district to start being aware of that threshold, try and preventative measures before hitting that 10% mark. We'd also like to recommend expanding targeted support for socioeconomically disenfranchised groups such as low-income students or people still learning English as a second language because, again, to our metrics, they were testing slightly lower all across the board. And again, to be clear, Mercer School District is a very well-performing district overall. Our objective is to identify where targeted support will be the most impactful and improve equity in the district and allow every student to stand on an even footing. Let's go to the next. And finally, we'd like to thank all the people who helped us with this, the Mercer Island School District team, as well as people at Seattle University, like our faculty advisor, capstone coordinator, and the Team Project Center. Thank you. Do you have any questions?
Questions?
So you focused on the GPA as your target variable, and you also showed that some math score showed a high correlation between improving that GPA. But I would guess that the students who score highly on that math score are also in a higher level math class. What's going on there? They're taking harder level classes.
Yes, I believe that's consistent. The idea here is that even still, if you score well, if you're scoring well on the test, you are probably going to be placed at a tougher math class. Now, that tougher math class might be like pretty difficult and might lower your GPA. Is that the suggestion you're making?
Yeah.
Right. I think my answer still is going to be that even still, the GPA remains high due to despite the difficult content. Perhaps the students have developed, stronger study habits, or as I hinted at earlier, perhaps they have additional supports outside of school that help kind of still buttress the grade to remain fairly strong. You don't have a visual for this now, but we actually see that as grade increases, GPA also increases. GPA also increases. Up till 12th grade, where you see quite a high GPA.
I'm gonna go in here a little bit late, but what defines low income for the students who are considered low income?
Yeah, I believe, and correct me if I'm wrong, what defines low income is if you are eligible for, I believe, free or discounted school lunch at checks, and that is like a separate check on your income. I forget what the exact number is, but if the family, if the household annual, if the AGI for the family is below a certain threshold, it might be set around 70,000 or so. But I'm not sure about the number, but that's how that was defined.
Other questions? Okay, I have a question for you. In your analyses, you saw a lot about individual factors like income or like absenteeism. How would your model have to change, or what would be different about your calculations if you were looking at intersectional factors? So for example, being both low income and a chronic absentee.
Sure. Just to clarify, you were meant to discuss this just in terms of what was it? In terms of how the machine learning would change? Okay. So for that, I think what we would do is what's called like feature engineering. Whether it be in the target variable or the predictor variable. Since you mentioned like the intersection between I think low income and something else, like maybe like constantly tardy. Let's make a new variable that's some sort of combination of them. So low income is like a yes no status. Chronically absent is also a yes no status on our analysis. So we could just have an additional box that says, okay, if you're both, we check it off here, and we'll see if the model prefers to use that one instead of the two component features. If it's like a numerical variable, we could also do some sort of scaling where, okay, maybe it's the number of days multiplied by, you know, low income or not, like yes or no, 1 or 0. I think that's how it would go.
Okay, we have time for one last question, if there is one. Okay, if not, let's thank our speakers again. Thanks. Yes. But it's like
Yeah, my grandma. Yeah. I don't know how it doesn't use that quick. Let's tell them how well we did. Wait, to be aware, let's find out before they back. Yeah, because my friend wrote that she has dyslexia.
Okay, thanks for your patience with our short technical error. We would like to welcome our team from Seattle U Athletics. So let's give them a hand.
All right, good afternoon. We are presenting on athlete performance prediction, modeling, and analysis. My name is Savannah, and I'm joined by Alon and Betsy. This year, we worked with Seattle University Athletics. They're an organization with 20 NCAA's D1 sports teams that compete in competitions nationwide. And they are also a member of the West Coast Conference, which is a group of 10 universities on the West Coast who have the Division I athletics programs. So the problem we were tasked with, we've got many data sources, but there's no streamlined way to get those data sources to useful information that coaches can use. So what do? Well, we started with the data. There are 3 sources that we used for this project. The first one is player data. Now this is a device that you can place on an athlete and it tracks their local and global positioning. So if you're in a basketball game, it'll tell you how far they ran, from where to where, how long that took, getting an idea of how fast they can move. And then the second one is talking dynamics. These are force plates, which are like 2 scales that you place one under each foot. And then the athlete does a big jump and it'll give you a great idea of their leg power, lower body strength. And the last one is output sports, which is a device that you place on a piece of equipment. They do some sort of deadlift or overhead press, and it'll tell you how fast that thing moved, and how long it took. So you can get an idea of strength from any body part, not just your lower body strength. Cool.
So before we move on to what we are doing, I want to talk about the challenges. So the athletics department used 3 different systems to collect data that you saw in the data sources. So they collect those data in a raw formats, and sometimes the raw data that they collect, it's not useful, and it's very hard to read for the coaches that what the measurements actually matters. So for example, one jump test from the force plate generates more than 300 matrices, which is hard for every coaches to understand, and each coaches use different measurements to adjust their athletes. So it is very difficult for us to figure out which numbers matter the most. And the second challenge about the athletes themselves. So the roster changes, changes every year. The new athletes comes every year. Some have years of data, some are new and they have a few weeks of data. So building a model which works for everyone. This is a challenge that we have faced. And third one is the interpretability. So our model can be perfect, but the coaches are the one who is going to use it, and they are not the data scientists. So our model can be complex, but it is needs to be useful for the coaches to understand what we are showing them. So if it's not, it's useless. So we just try to put all our models into a dashboard. So next, the models that we have used.
Okay, so now that I've seen the key data sources and challenges, these are the methods that we have used across the whole project. So first one is the empirical base. So here we are forecasting and we are trying to understand, given the current data, how do athletes perform the next weeks. And then the clustering is the main objective is to group athletes based on features. And then we have PLT model with the stage point detection, where we are trying to flag any unusual behavior across athletes training. And then the last one is principal component analysis, wherein we are trying to understand with the given minimal data, how do we kind of get a better insightful data analysis. So moving into the clustering. So the main objective of the clustering was return to play feature. So what do I mean by that is trying to understand those athletes who are ready for matches, those athletes who kind of need more training, or more importantly, those athletes who are not performing given a particular threshold.
So like you can see, this is a technical analysis, and the main features which goes into this clustering is can be divided into three groups. The first one is normalized features, wherein we are trying to understand each and every athlete's features by per session, so that we don't over dominate the clustering. Then the second one is athlete related features, wherein we are not comparing the athlete metrics to its whole team, but to its own relative baseline features. And then the last one is week to week changes, wherein each and every athlete week to week is he kind of improving or declining. Taking into consideration these three groups, this is the technical analysis, and this kind of puts these particular athlete numbers into groups. And like we can see, the vertical blue line, there's three vertical blue lines, which kinds of indicates that 3 is the ideal number of clusters from this technical analysis, and we can come up with the analysis of 3 is the ideal number. So going into the next, the main challenge was to kind of put this clustering into more approachable or more interpreted on the go analysis for the coaches. So this is the visualization which we came up for the men's basketball. So these three clusters, or these three groups are actually three clusters. It is divided into match ready, building load, and restricted. Which kinds of means that the match ready athletes are those who are like ready to go for the matches, who have the highest salary athletes, which is followed by the building load athletes, and then they're restricted. And then on the x-axis, we do have the week by week comparison for Jan 19 and Jan 26. The most important and the beautiful understanding of this visualization is, like you can see the data points which is marked across the black circle. Those kinds of indicates that there is a change in clustering or the athletes. And this kinds of gives question for coaches to kind of understand how can we better these athletes and push them all eventually to match ready cluster. Okay, this slide shows our archetype clustering output. There are two views here, the squad overview on the left and individual athlete overview on the right. We took over 300 metrics per jump used for PCA, principal component analysis, to compress all of those down just to two numbers per athlete per week. Think of it like a fingerprint. Those two numbers becomes the axis of the squad. PC1 is the horizontal captures impulse and load tolerance, how much total force is being built by an athlete over their ground contact, and through a longer and more deliberate counter movement jump. And PC2 is on the vertical captures, explosive and reactive power, how fast, ballistic, and powerful the jump is. And every dot is one athlete in 1 week. Athletes who land closer together stay at like a closer physical profile. And archetype clustering just means we're grouping all of them together, like athletes by how similar their physical profiles are, not by their sport or not by their performance together, but how their body movements and performance in the jump. So two athletes from completely different sports can share the same archetype of, if their neuromuscular profiles looks the same. That's really useful because training recommendations can be based on how an athlete is actually moves, and rather than just what position they play. And the trajectory of an arrow shows the direction of changing throughout the season, and drifting left means the athlete is generating less total impulse, and drifting down means that declining in explosiveness or reactivity. And some athletes stay tight around their baseline, and others show clear seasonal drift, and that drift is real signal about their body is responding to the training loop. And this slide is our forecasting output, and it shows exactly why we built two models instead of just one. Left panel is force endurance and right is explosive power. Orange is the actual observed data, and the colored lines are our two forecast methods, in which ARIMA, which projects forward based on their past patterns. Think of it like a weather forecast, and Bayesian model, which starts with knowledge of similar athletes at the same position, updates as the data comes in, like an experienced coach drawing on past players. We combine both into an ensemble for a more robust prediction. And the shaded region is the 80% confidence interval, where we expect the true value to land. And the agreement in the top right shows how closely the two models are aligned, 98% on the left and 45% on the right. When they diverge like that, it means the metric is harder to predict, and the system flags that uncertainty rather than hiding it. Stiffness was the hardest forecast across all the three sports, and honest finding that we stand behind.
So what is change point? So the terms sound technical, but the idea is simple. Every week, each athlete trains, and the post split just record there how hard they work. So most of the weeks, the number goes up and down a little. So that is normal, but sometimes the change is not normal, and the change is not normal. It is real. So that real change is because in the changes sometimes the change is normal because the athlete is not recovering and they are just having a tired day, or sometimes the training plan change. So this the terms stays down, and it shows on the negative side. So it's it's the change point. It's what the change point it is. So it's actually that week when the change is happening. So if you see on my right hand side, we take the two athletes from the men's soccer teams, and in which we just did a change point detection on the session load of their per athlete. So in which the colored ones are the per athletes, and the gray lines are the average of the top three performers of the team, which we are comparing against each player. And on the left hand side of my, and there's a purple line which shows the gap, which is the difference between the athlete and the benchmark, and the yellow line is the average level between before and after the changes, and the red line you see it's a real change point that our model has detected. So if you see on the upper plot, the athletes in the starting of the season there is a negative, they have negative changes, and after that out in October, after the change point the number goes up to 0, which is they are just shifting towards the uh, close to the benchmark. And on that, if you see on the below plot, the athletes has no change point, and it's working steady all across the season with the benchmark athletes. So the algorithm we use is PELT, and it just each scans every athlete and flag automatically the what's the and it flags automatically what the change point it's happening for that athlete. So it's easy for the coaches to read through those change points instead of reading the 100 of charts. So if there is a gap, so the coaches can look into before the players to get into matches that the player is not getting doing well, or sometimes the player is not uh, uh, moving and properly. So and we also tried this change point detection in the different matrices as well, like acceleration and deceleration as well. So in this, sometimes because sometimes the athletes runs the same distance, but the acceleration drops because they are working on the less intensity. So this is a hidden factor as well. So our models can find that as well. So we just put all our those things into a dashboard.
And this is the coach facing dashboard. Athlete 1354 is pulled up, and he's from men's basketball, flagged as high load explosive. Below are the 8 metric panels, like each showing the actual trajectory and the 2-week forecast with confident bounds. And the strength coach at 7 a.m. doesn't need a statistics degree to use this. They see the trend, they see where it's headed, and a flag appears if a meaningful decline is predicted. All the complexity in PCA, to forecasting trends, confidence intervals, change point detection, and athlete clustering is happening under the hood, and the coach just sees the athletes.
All right, how does this help coaches? So with predictive modeling, we can help coaches make proactive decisions instead of reactive decisions. So if an athlete is starting to head into a downward trajectory, we can step in and help them before they get injured. Coaches can also use this to place their strongest players at the forefront of competitions. This project will be handed off to future capstone groups. So some of the directions we think could be taken are adding in more data. As more seasons of athletics get recorded, we will have more data to build more robust models. This can also be expanded to more athletic teams. A last couple ones is we can use seasonal arena models, which would be using last spring's data to use as a baseline for this spring's models. And last one is separating training data from game day data because there are different pressures in practice versus competition. So treating those as two separate things would show some interesting analysis. Thank you so much for joining. We would like to thank a few people, Dr. Matt Hockey, who was our sponsor liaison, Dr. Zhang, our faculty advisor, Dr. Mandible, our capstone professor, and Kyle and Sarah, who were on the performance and medical staff and gave us great insight onto how coaches use this in their practice. Any questions? Thanks.
Okay, questions? Okay, so I have a question for you. In your clustering, specifically your hierarchical clustering, how did you determine that 3 clusters was the appropriate number? And could you do a little bit more explanation on the interpretation of those? How do you know that some players are match ready versus others are still in recovery? Yeah, sure.
So the first question to identify the number of clusters. So if you look at these 3 vertical blue lines, so these 3 kind of indicates that these group belongs to majorly to this point. So we can kind of sense that these 3 vertical blues are kind of indicates that and is the ideal number of clusters we could form from this diagram. That is how like we kind of feed this diagram. We can kind of say that if we pass like vertical, like if we pass a big horizontal line, what is like the number of those which can cut equally, and more importantly, if you have 3 vertical lines, we can kind of, if we count the 3 vertical lines, then we can say that right, and looking at this, we can understand that 3 is the number of clusters. And then going to the next visualization, so this visualization just basically puts the clustering. So each and every features that you kind of look into consideration. This basically it's like multiplying the number of features, and if anything is like if it's a match ready state, the athletes are like have the highest number of metrics out of all the metrics which we have considered, which is then followed by building load and then this. So this is basically like saying, hey, if 1352 has the highest number, and then like 1041 kind of has some of the features which is lower than 1352, and then followed by these aspects.
Let's thank our speakers one last time. Okay, our last team in this session is an undergraduate computer science team, so let's welcome them. Their sponsor is Cost.
So hi everyone, we are the Cost group and we have built READEASE. Our team includes Eric, Andrew, Rohit, and myself, Alyssa. Our faculty advisor is Professor Yang, our sponsor is Anthony Washington, and our sponsor tech lead is Jaden Davala. So first today, we'll introduce you to our sponsor Cost and then our project READEASE. Second, we'll go over all the new features we implemented, a new security update, and the new UI. Third, we'll go over testing that was done on the site. And fourth, we'll go over the services we use for implementation and deployment. Fifth, we'll show you a demo of the site, and lastly, we'll go over our future vision for READEASE. So Cost CEO Anthony Washington recognized that the traditional education system often overlooks the needs of individual students. His mission and the company's mission is to ensure that every student feels empowered to succeed regardless of their needs. So with READEASE, our mission was to create an adaptive and supportive learning environment for both students and their teachers. This isn't just about a tool, but a future where every student feels empowered to succeed regardless of their needs. READEASE is an educational reading platform designed to bridge the gap between classroom instruction and student independence by providing accessible learning tools for all its users. The first of these tools is our interactive assistant. Its goal is to make the site easier to use, and so it provides directions on how to navigate the site and use its features. On either the students or teacher side of the site, there's a list of buttons with all the features on that side of the site. Users can select which feature they need help with, and they're provided with step-by-step instructions on how to use it. Second, we have flexible assessments. The original site only supported multiple choice questions, so we wanted to expand this. We've now added fill-in-the-blank, short response, and paragraph response question types. When teachers are creating an assessment, they can select the question type they wish to use from a drop-down menu. And when students are taking an assessment, they're given various size text boxes to write their responses in.
Next, we have chapter detection. This feature will allow students to see and jump between the chapters of a book. So when a student goes to begin reading a book, there's a button with options to open or close the table of contents sidebar. When you click on one of the elements, it will jump you to that page in the book. This feature will be generated for all of our books automatically, so when we add new books, it won't require any additional work. And fourth, we have our audio recordings. This feature allows students to record themselves reading, and lets teachers then review this recording and provide feedback to the student. So again, on the reading page, there's a box here with options to start, stop, and submit their recording. When a recording is in progress, a timer will appear at the top of the screen showing the elapsed time. Then, once our recording has been submitted, both the student and teacher can listen to it and, of course, see the feedback that the teacher has given. And for our final feature, we've added the goal tracker. This sorts goals into 3 steps, either not started, in progress, or completed. Teachers can assign these goals to students, and then students, as they work, will complete them. Yeah, I think that's it. Sorry, there's a little bit of this. Moving on for our user-facing changes, we've also improved the security of the site. This focuses on 2 main aspects. We're user authentication and request validation. For user authentication, we're using HTTP-only JSON Web Tokens, or JWTs. HTTP only prevents against JavaScript attacks from other sites trying to mimic READEASE and steal the token. While the use of a JSON Web Token as an alternative to simply handing over the username and password, it decreases the likelihood that critical information is stolen, and a token, if stolen, only provides limited access to the thief. As for our request validation, we are now checking that whenever a user makes a request, they are actually allowed to perform that action. So for example, we would not allow a student to modify an assessment.
Alright, so for the user interface, we redesigned the UI to make sure it's more modern, and we also implemented WCAG 2.1 AAA standards. While most platforms typically target WCAG 2.1 AA standards, we targeted AAA standards to make sure that it met the highest accessibility conformance level and to best accommodate and support students with reading disabilities or any form of reading challenges. So the first thing that we did is manual testing. We made sure that every component in the application was functional, and then we did two forms of accessibility testing. We tested the WCAG, which stands for the Web Content Accessibility Guidelines. We tested the color contrast for it to make sure it met the AAA standard. We basically tested every single component in the application when it came to like form, fields, text, backgrounds, and buttons. And we also tested hover indicators and focus indicators to make sure that the website met the WCAG 2.1 AAA standards. And we also tested the application with two different screen readers. For Mac OS, we used Apple VoiceOver, and for Windows, we used NVDA. So for our tech stack, for the front end, we used React.js, and for the back end, we used Node.js and Express. In order to save our versions and in order to work through different branches and different changes, we use GitHub. And our sponsor for deployment is going to use Docker, Railway, and Supabase.
Now we will show a quick demo of our app. Alright, so now here we can see the teacher side of the READEASE app. Yeah, so here's the teacher side of the READEASE. Here. Well, yeah, so here's the teacher side of the READEASE app. On the top right, you can see there's a little question mark which you can click on that takes you to the interactive assistant. And here the teacher can click on any of the buttons to learn more about how to use the site. And if we go back to the dashboard, on the left, we have all the students which are assigned to the teachers. The teacher can click on any of the students to view their progress. And here we can see Olivia. On the left, we have all the goals that are currently assigned to the students, and we can see their current status so far. On the right-hand side, we have a graph of the assessment scores, which are all the scores of the students on the assessments over time. When we scroll down a bit, we have the recording history. Here, the teacher can play back and listen to all the recordings the students have recorded so far and give any feedback if they want. Now, moving on to the right-hand side, we have the assessments. Here, the teacher can click on one of the assessments to open it up, and they can see information on the assessment, such as the book, the students, and the questions so far. The teacher can also edit the assessments if they want, for example, adding new question types. As you can see here, you can see all the different question types that we implemented so far. Now we can log out the teacher side to go back to the student side. Now logging into the student side, here we can see the student view of the READEASE app. As you can tell, it's pretty similar to the teacher side with a few changes. Again, on the top right, there's the question mark which they can click on, and it will tell them and leads them to the interactive assistant, which they can click on to figure out more about the site. On top, we have the goals that are assigned to the student. Here, the students can see their goals and their progress so far. They can also filter the goal by their status and sort by newest to oldest. Now, for a book section, the student can click on any of the books that they want to read. For example, here we have Charlotte's Web. If you scroll up, there's also a table of contents, which the student can click on to view all the chapters in the book. They can click on any of the chapters to jump to the chapter directly, which allows for quicker navigation. At the very bottom on the left, we have the report section that we implemented. Here, the students can record themselves reading the book, and they can also submit this to the teacher for them to listen. Now, on the right-hand side, we have the assessments for the student side. Here, the students can click on any of the assessments to take. and they can see all the questions and fill out the answers however they like. And at the very bottom, we have the recording history on the student side. Here, the student can play back any of the recordings to listen to themselves speak, and they can also view any feedback they receive from the teacher. Now for the future vision, we have a few ideas on how we could continue to improve READEASE. One is automatic and manual grading for assessments. Since currently we only have automatic grading for multiple choice questions, we would also have to implement manual grading for the written response questions. Another is a goal tracker AI. Since right now all the goals are created manually by the teacher, which is pretty tedious, it would be good if we could have an AI that could create goals automatically for students. Lastly would be a book generation AI. We could also have an AI that would create books based on the students' reading level so far. So in summary, we already thought group and we're working on the READEASE application. The 5 new features we implemented this year are the interactive assistant, flexible assessments, chapter detection, audio recording, and the goal tracker. We also improved the security of our application by implementing JWT authentication, and we also updated the UI of our app to make it look more modern. For our tech stack, we used React for the front end, Node.js and Express for the backend, and we also did manual and accessibility testing. Lastly, we also discussed our future vision. Thank you.
Does anyone have any questions?
Yeah. I can just speak out. Okay. For the recording feature, is it possible for students to like re-record, or do they just have to like record and submit like first try?
Yeah, so once they hit start recording, it'll record whatever they say, they can click stop, then they can submit. If they decide they want to re-record, they can just click stop without submitting, click start again, and it restarts the recording.
Could you tell me a little bit more about what that accessibility testing looked like? How did you gather the data for that?
Okay, so there was no automated accessibility testing as of right now, but I did do manual testing to make sure that so basically it was just manual input and just like using the screen reader manually just to play kind of as the perspective of someone who's visually impaired. Just that's also kind of the reason why I did this accessibility testing, using these 2 different screen readers. And also I did do use a color contrast like application to basically check like the color contrast for each component to the application. So that's how it was done. So it was mostly manual. It's pretty much all manual.
Thanks. I'm curious about your chapter detection tool. Is it does it use computer vision to just look for the word chapter and then it marks that, or does it look like, what if there's an author who like doesn't like to use the word chapter, it just has like Roman numerals at the top of each new section? How does it go?
Yeah, so for that feature, basically we use regular expressions to implement it. So we'll just like try to search for the words chapter throughout the book, and if it finds that, it will have that as a chapter. So like you said, sometimes it's not like 100% accurately, like 100% accurate if like it doesn't say the word chapter. But you can do it.
That's adding on to that briefly. I'll also note that as we do intend to add an AI to help for book generation, that will help to curate and make sure that we do follow one standardized format, in this case, chapters, page, no.
Other questions? Okay, let's thank our speakers one more time. So we have, that was last talk in this session, so we have a 15-minute break and we'll come back at 15 for more MSDS. Okay, we're gonna go ahead and get started with our last session of the day. This session will have 3 MSDS talks, all from our larger corporate sponsors, Costco and Amazon. So let's welcome our team from Costco.
Hello everyone, we are the Costco Wholesale team and we have worked on the retail price analysis and recommendation engine. I'm glad that everybody's here today. I'm really thankful for our sponsors, Costco, for sponsoring this project. It was a great learning opportunity. My name is Salman and I have here with me my teammates Javitha, Sonia, Maria, and Chris. Let's get started. So, walk into Costco and what you see is a warehouse. What you don't see are the decisions behind it. Thousands of pricing decisions made every single day across hundreds of product categories, each single one carrying a real commercial consequence. Costco processes millions of transactions daily, and each transaction is a moment of agreement between Costco and a consumer. This product, this price, right now. Multiply that across every item, every store, every day, and the scale becomes staggering. That is why pricing at this level is not an intuition. It is one of the most consequential decision problems in retail markets. And that decision is harder than it looks. Let's give an example. If you price something too high, the customer's trust starts to erode and the customers start to walk away. The sales volume drops and the revenue erodes. If you price it too low and you're leaving money on the table and opportunity starts to disappear at a massive scale. There is no neutral choice when it comes to pricing decisions. Every price is an active decision that makes a direct impact on the business. And this problem is not unique to any one company. The world's largest retailers like Costco, Amazon, Kroger, Walmart are all actively wrestling with this. It's a problem so important that they have multiple teams dedicated to just pricing. But why? Why is this so important? Pricing decisions off by just a few percent doesn't just mean a little rounding error on your end of the year balance sheet. It's hundreds of millions of dollars of lost opportunity cost. So the big decision isn't whether pricing is important, but how do you do it well and how do you do it well at a large scale? That brings us to the core question of our project. With all of that money on the line, how? How do you actually find the right price? Not the one that protects Costco's margins, not the one that beats a competitor, but that sweet spot that earns customers' trust and maximizes sales volume. That is what we set out to answer.
So, before we get into find the best price, let's talk about who is this problem really for. It's Costco Wholesale. It's a multi-billion-dollar global retailer with 900 plus warehouses and 145 million plus members all over the world. And these members are not just customers; they are trusted, and they expect value, and they trust that Costco will deliver a promise every single time they walk through the door. And that promise is to provide great value to its member. And Costco is making that promise in one of the toughest competitive environments where companies like Walmart, Sam's Club, Amazon, Kroger, etc. are competing for the same customer. And this is the world where Costco operating in. And this brings us to the obvious question, what does Costco have that other competitors don't? So it has two things. The first is a Costco management model, which creates a uniquely loyal customer base, but one with higher expectations. And the second one is Costco's commitment to provide the best optimal prices, which means there's a very little room for the errors. And they cannot overprice the way out of the mistake at this scale. So each decision has to be precise. That is why a pricing approach matters. Now let's check what happens when price changes.
Okay, so let's understand this with an example. So think back to early COVID when people were rushing to Costco or any wholesale retail, buying paper towel, eggs, sanitizers, and prices went up, shelves emptied anyway. So that's called inelastic demand. Prices didn't really matter because it's a need. Now think about the same time. Did people buy any fancy snacks or any non-staple products? Not really. They either cutting back or switching to the cheaper options. So that's called elastic demand. So it's a want, and people are very sensitive to prices when buying wants. So that's the whole idea behind price elasticity that we set out for Costco. Okay, so where did we start? We started with real transaction data, not the guesses, not the surveys, actual sales volume from Costco and the competitor stores across 18 Washington warehouses, spanning data all the way from January 2021 to April 2026, and three focusing categories, that is paper towel, olive oil, and eggs. But raw data is messy. Think of it like a recipe. We just don't dump everything in the bowl. We have to clean bad eggs, zero sales, weird formatting, duplicates, and we have to normalize the prices so that we can actually compare prices across each retailers. So once we are done with the cleaning part, so how we can model the clean data into the log regression. So let's understand this with an example. So before 2022, the egg prices were very stable. And 2022 hit, you can see the egg prices went up because a bird flu wiped out millions of chickens and prices shot up. So here comes an interesting question. Did people stop buying eggs? No, they didn't. They keep buying the eggs, but they quite complain. So instead of tracking dollar change, we asked one question. If price move 1%, what happens to the demand? And that's where the log regression answer this question. So white eggs, which is considered as a staple product, and people love to buy white eggs. For every 10% increase in white eggs, the demand dropped by 5%, which is barely a reaction. However, brown eggs, people love to buy brown eggs, but the moment prices spike for brown eggs, people switch to the white eggs. So for every 10% increase in brown eggs, the demand drops by 10%. And that is a flexible reaction, but balanced. So that is we have something sorted out for Costco, and we get to know that where is pricing matters, where it doesn't. So let's see what results we have achieved for Costco using log regression.
Okay, so let's take a look at what we actually found for Costco's products. Looking at eggs, own price came in at negative 0.747, cross price elasticity at 0.968. This just means that members buy eggs because they're a need, they're a necessity and a staple. And this gives Costco some pricing stability and leverage, given that there's not significant responses to price changes. Olive oil was slightly more elastic. On price elasticity was negative 2.39, cost price negative 4.07. This means that members are more actively comparing value and responding to the pricing signals. Costco still has pricing stability here, but they just have to be a little bit more careful and deliberate with their pricing choices. And one thing to note is that the cross price elasticity for olive oil is negative. That's just a result of our data limitations with synthetic data. But now that we have a rough idea of how elastic each product is, how does that translate into actual price recommendations? When our optimization model sets a price, it has to meet three constraints simultaneously. First is demand. Will members actually buy more given a price decrease? For something like eggs, a 6.5% decrease was projected to have a 5.2% increase in sales volume. The next is economic sense. Costco's recommended selling price still has to be more than Costco's purchase or manufacturing price, given that revenue has to be consistent and healthy, but overall positive. And then lastly, competitiveness. Costco selling eggs at 38 cents versus the competitor ceiling or competitor price at 46 cents. Costco is still definitely competitive and providing members more value, which is the goal. And all three of these constraints have to be met, given that is what keeps the pricing disciplined. And this is a summary of our recommendation. The bar plot on the right shows weekly predicted volume lift for the past couple of months, just to show that demand's gonna keep changing. It's not gonna be the same demand across all weeks. The table on the left shows the recommendation for our latest week, which is April 21st to the 27th.
For eggs, like I mentioned earlier, price change of 6.5% was expected to give a volume lift of 5.2%, whereas olive oil with a smaller price cut of 4% was projected a larger 10.1% volume lift, which makes sense given olive oil was found to be a bit more elastic than eggs. And then looking at the recommended price versus the competitor price or the competitor ceiling, we can see it sits comfortably below the competitor ceiling, but not unreasonably low relative to the current price. And so in essence, this is what a pricing manager would receive or see on a weekly basis, a product, a price, and the forecasted demand outcome. And for a more in-depth look, let's move on to the dashboard example.
So, after building elasticity and optimization models, what's next? How do we make these results readable for the real pricing team? So let's imagine you are a product manager, and do you really want to manually interpret all the CSV files and go through all the notebooks? No, you definitely need a view to help you decide what to review, what to validate, and what to trust. And that is why we built a dashboard. This is how a dashboard will look like. So this dashboard answers all the practical questions that a typical pricing team would ask. Like, what is the product that we want to review? What is the Costco set price? What is the model recommended price? And is the volume lifting or decreasing? So a typical user would start by selecting a product. Let's say I would choose from eggs, olive oil, or paper towel. Once the category is being selected, the recommendation has been popped up. So this recommendation readout generally shows what's the current Costco price, what is the model recommended price, and what is the expected volume to be lifted. And what is the expected volume to lift. So this combines all the pricing context into one dashboard, and it gives a clear view to the pricing. But once the prices has been read out, all the recommendation has been read out, what's next? Do you want to blindly proceed with that model recommended price? You definitely want to check out for some warnings. So let's say, for example, X. There is a validation before action warning. It means that model suggests a price, but there is the price is outside the safe bar. So it asks the pricing team, instead of taking any blind action, review the flagged issue and then proceed with it. So instead of asking someone to interpret the technical model, we have built a pricing system workflow using Streamlit, which gives analysis into a user interface, and we definitely want to make that work shareable. So we use Elastic Beanstalk to make that work shareable.
Yeah, so this brings us to the penultimate question. What does this exactly mean to Costco? So we started first with a question. How do we find the right price to maximize the sales volume? Then our approach was to utilize the log elasticity model on real world data. And then we put those log model inputs into the optimization model to volume maximize price within certain constraint bounds that we have set. And our deliverable was to be able to put it on a dashboard for the pricing team to utilize. So we started with a question that every price has a decision. Well, now Costco has a better way to make it. Thank you.
Questions? Okay, I have one question. If you needed to incorporate long-term factors, so let me justify that. If I go to Costco and I'm at Costco and I know I need eggs, I might buy eggs at any price that Costco's selling them. But long-term, I might say, hey, I'm sick of paying those prices. I'm now going to switch my behavior. So long-term decision-making might play more of a role rather than just eggs are this price this week and I will or won't buy. How might you change your model to be able to incorporate those kind of longer-term decision-making things that customers are doing?
I think that is a very tricky and hard question to deal with, definitely. I don't think us as a consumer and a member daily really know what we want to buy and necessarily not really long term. To incorporate those long-term changes, our current optimization model is running on a weekly cadence. So what that means is we're essentially inputting what we predict or what we think the maximum volume price would be next week. So essentially, even if there is a long-term change in customers' mind, I think that will be captured within that weekly signal is what we are hoping to determine. I believe, though, as you mentioned, that is a really hard question just because the customers and the consumers aren't really aware of what their own long-term purchase behavior is going to be, just because the market itself is changing a lot. For example, even with oils currently, like gasoline, I don't think anybody could have foreseen that the gas prices are going to rise. So like a couple months back, and so they're now wishing maybe they want to be, but yes.
Are you suggesting like a price change on a weekly basis? Because looking from a customer view, if the prices keep changing in front of me, it's more difficult for me to remember what I would like what I expect. So also warehouse technically looking into people adjusting the etiquettes and everything, so that's effort on the employee side might be also considerable factor. So do you suggest to change the price every weekly or once in a while?
That's also a fantastic question. This is actually within also Costco itself, in that they want to prioritize that customer integrity. The customers and consumers do not want this changing price each week. I don't know what the price is going to be last week or this week or next week. So this factor itself for us was very huge. And since we're also basing a lot of these optimization on the competitor's price, when we're putting in the optimization model, we're putting in those certain types of constraints, setting these bounds, saying that we don't want this price to necessarily change each week. We can have it run each week, but for whenever we do need to run it, we're forecasting for that future week. We don't have to run it every single week, like how we showed it in our graphs. We can, let's say if we foresee, we can run this model, oh, there might be a volume increase if we drop the price or increase the price. How will the pricing managers act on that decision is up to the pricing managers and within the Costco's internal team to really decide that factor. But as I mentioned, Costco is really keen on this customer integrity, so they're not looking to change prices, is what I would assume.
Okay, one more brief question.
So why did you pick eggs? Why you didn't pick something from different type of product?
Right. So the three products that we chose were eggs, olive oil, and paper towels. These are what the retail markets call as fast moving products, which means they are purchased in heavy volumes, come into the warehouse, and then a lot of consumers buy them, so they leave their warehouse at a very fast rate. This is a good example because we don't want something, I guess if we look at something that sits in the warehouse for a long time, it means that demand for it isn't as rapid as some of these fast moving products, which can see how the demand and the sales volume is changing per day more rapidly compared to some of these products that are staying in the warehouse for a very long time.
Okay, that's all the time we have for questions, so let's thank our speakers again.
Because also as right, like a provided other everything forecast and like behavior talk because various like like which one is all about the agency it's not a one man briefing, right?
Okay, our second team presenting in the slot is MSDS 26.2 with Amazon.
Hello everyone, welcome. Today we are going to present our caption project sponsored by Amazon Worldwide Sustainability. It's called the true cost of waste. Like in simple language, every day whenever Amazon gets a product returned or overstock, what does it do? Like what should be done with it? And we are going to find out what is done by Amazon people with that products. Let me give you a quick introduction. Here we have Dan, Tyler, Roger, and Nikhil. And throughout this six-month process, we had our advisor, Dr. DLICT, and from Amazon, we had Hugo and Dennis, who supported us to complete this project, and we are very grateful for them. Let me give you some context about Amazon Worldwide Sustainability. They are not only telling go green. From last few years, they are massively doing it in a large scale. They have delivered 1.5 billion packages by electric vehicles. They have delivered 81 million food to the people in need. And they have in all over the process, they have reduced their waste diversion rate to 83%. And the big commitment they have given by 2030 is they want to reduce food wastage by 50% in all US and Europe. And this project is the stepping stone for this commitment. And for the problem statement, like in everyday life, Amazon faces a problem with their inventory. The problem is the products are overstocked, about to expire, not good to sell. Like whatever, it should not go in the market. So what they do, there should be a decision taken with the Amazon team, and the Amazon team takes the decision, liquidate it, dispose it, or sell it, or donate it. So about this process, in this project we have we incorporated and quantified the cost of waste to that decision making process. In that way, the Amazon people can find a good way to order any products, sell any products, and they can take better decisions while considering any single product step.
Okay, so before we can price waste, we'll need to predict it first. In this section, I'll go over how we built a model to estimate the likelihood and the magnitude of items entering the recovery funnel. We start with the data. We spent 4 years of recovery funnel records, going from 2022 to 2025, totaling about 60 million raw records in total. We aggregate our data down to the site, the product groups, and the week level. This is the lowest resolution where interventions can occur. And as a result, we end with 6 million training observation. Now, each of our records carries information about the units volume, the weight, the cost of goods sold, whether or not the items is managed by Amazon entirely or it's from a third party and fulfilled by Amazon. There's also some information about high-level information about what the product is, whether it's food or not. Now, these raw features alone don't give the model a sense of trajectories. So we engineer a series of temporal features, 1 week, 4 weeks, 12, 52 weeks lags, and rolling means. These give the model, allow us to differentiate between whether or not the site is trending towards high weight recoveries or is going through an anomalous spike.
Two things we didn't have. We don't have detailed information about what the product is, what's it made of, what's the shelf life, as well as the site operational metadata, like how many people works on that site, what's the scale of that site, what's the level of automations involved. Those would be important in terms of understanding how all of this ties to the amount of waste that our recoveries that we're getting, and will be flagged again in our limitation. Now, our data carries three distinct structural properties that make a single model the wrong choice. First of all, the rates of items entering the funnel is zero inflated, meaning that most of the time at a given site, the majority of items are sold, or they will not see any items entering the funnel at all. This is in line with the most common business scenarios where the majority of items are sold and not returned or not overstocked. Secondly, among the non-zero observations, the distribution span the entire 0 to 1 proportion range with masses at both ends. And then finally, as we predicted the rates of items entering the funnel, we need to decompose that into 5 different outcomes, whether it's return to vendor, discount sales, liquidations, donations, or ultimately landfill. These need to sum up in a consistent way. So our solutions is to decompose our problems into 3 stages. The first one is a binary classifier. It's asked and answers a simple question. Did any items enter the funnel at all this week? The second one is a regressor trained only on the non-zero observation that predicts the actual rates. And finally, a series of 5 regression model for each of the 5 outcomes would address a softmax normalizations that ensure they all sum up to the predicted rates in stage 2. Now, for all the 3 stages, we use extreme gradient boosting for our models. The primary reasons, it's robust with tabular data, which we have very wide table. It's also handles null value natively, which we do have a lot of sparsity in our data. And the gradient boosting natures, and as well as the resilient tree natures of the model, have captured non-linear interactions way better than linear alternatives. We use temporal slip for our data. The first 3 years being used as a training set, and the last year is the evaluation sets. This respects the time series natures of our data and prevent leakage. We perform hyperparameter tunings with Optina 3-parser estimator as opposed to research to optimize our compute time. And finally, we use Shapley values for our feature importance. The additive natures of Shapley values serve as the underlying principle on how we translate our predictions into actions that the organizations can take. So to go over that, thanks to Shapley values, we can decompose our models into 2 components. Each prediction carries information from the historical baseline, the 26 and the 52 weeks and rolling means, as well as the shift that happens within this week, whether there's a spike in the volume of the units, or whether or not there's a spike in the shares of retail and fulfilled by Amazon items. As a result, predictions that lean heavily on the historical features point to a structural properties of the site or the products that warrants a high-level strategic interventions, whereas predictions that relies mainly on the deviation component could lead to action that the local team can take.
So we built the model now to see if it actually works. Remember that our model has 3 stages. The first one being the yes or no question. Is any recovery going to happen at all? On the left side, you can see that our model gets that prediction right 94 times out of 100. Once we know if any recovery is going to happen, we move on to stage 2, which answers the question by how much. On the left, you see the MAE, which is how much we're off by. And on the right, you have the R-squared value, which is how much variance is explained by our model. On the second stage, those values are 0.04 and 0.86, which are very respective. And combining both those stages for a full pipeline, the MAE drops down to a 0.03 and our R-squared sits at 0.68. Now that we know if any recovery is going to happen and by how much, we have to now pinpoint exactly where it's going to land. What you're looking at right now is our 5 different recovery channels along with their mean absolute error values. To give some scale about the numbers here, our model ranges from 0 to 1 in here, so a value of 0.085 mean absolute error is very respectable. One thing to note here is the differences in MAE values between the channels. We notice that our model does a better job at classifying the smaller channels, whereas the bigger channels like disposal and return to vendor
have larger volume and larger variance, which our model can start with. Now that we know that the model is accurate, we have to know if it's accurate all the time or if it has blind spots. What you're looking at here are the recovery fluctuations of two product groups across a year. The black line represents actual data, whereas the red line is our predicted model. You can see that our model is basically spot on in mirroring the trends throughout the year, which you can imagine giving this to an Amazon facility manager and how this can impact the inventory decisions they make. Knowing what products are at risk at what time of the year can significantly reduce potential waste. One thing to note here is on the bottom chart, you can see that the black actual line is spiking up and down, while our predicted is sitting between those peaks and troughs. This is our model performing some hedging where it's being more cautious around the extremes, around the highest variance of the model, which also makes sense from a business perspective because you would rather under-predict those extremes rather than over-predict them. But model that only gives you just a number is not very trustworthy, and we need to explain where these predictions are coming from. One thing to quickly note here is that labels on the left, like product is round, box as a sticker, are not the real drivers of our predictions. Those would be the confidential Amazon data. So what we put here is standards for those values, so to make you understand how you would read this if you have the real data. How this works is the labels on the left are things that the model looks at. The dots are data points, and if the data point sits on the right of that line, it pushes towards recovery. If it sits on the left, it pushes away. The colors describe if it's a low or a high value. So putting that all together, how this works for package weight, for example, is if you see those right dots heading to the right, you would say product that has a high package value would tend more to end up in recovery. So that's where we are right now. But what can we do to improve? Two things to understand is that using our real predictors and our real drivers, we notice that the model's mainly learning from history. This makes it a very good predictor given the old data, but it can struggle if it interacted with something new. The second thing to note is that we were given scrambled and sanitized data to protect Amazon confidentiality. This means that we don't know what the product group represents and where does what the sites represent. This doesn't limit us in predicting and from the model perspective, but it does in interpreting and answering the why question of these predictions. And how we can improve this? Mainly richer data. Like I mentioned, we would need more information about product descriptions, material compositions, and more site descriptions like facility type and proximity to their partners.
Right, so now we're going to move on to the cost of waste. In the interest of time, I'm going to be fast, so pay attention. If you have any questions, you can ask me at the end. So first, for the business use case, the propensity models gives us probabilities, right? And you can look and you can sort of use this to inform an intervention analysis. You can see where is the probability of waste the highest, right? But this probability isn't necessarily the best metric because it's not directly tied to business impact, right? So we instead want to use dollars. So the point of the cost of waste model is to assign a dollar impact to these waste outcomes, and then with both of them, you can have an expected financial impact, right? So what you need to understand about the inventory life cycle is that it's not a pipeline where you consistently move towards an end goal in a linear fashion. You can have branching, you can have cycles, right? So it's sort of this web of possibilities, and in this web of possibilities, you have valid pathways that can happen, and among these valid pathways, some are more probable than others, right? So there's these characteristics of cycles, nonlinearity, and the distinction between what's possible and probable. Right? And the way that we model this is by encoding the inventory life cycle with a graph. So what you see here is these states are what are called vertices, and you have edges between these states that indicate valid transitions, right? These edges will be parameterized by both a cost associated with the transition as well as a probability. So the size is supposed to convey a general sense of which ones are most likely. Most common pathway is that you're sold and not returned. That's why those are the biggest. And an example of a cost attached to these edges is maybe from sellable inventory to sold, you'd have the transportation. Right. Now, the graph structure can answer local questions like, given that we're in a state, what are the next states we can go to? Which ones are the most probable? What are those stepwise costs? But we're ultimately interested in global metrics like what is the total cost, not just a single step, over the entire life cycle. So the way that we bridge this gap is with what are called random walks. And basically what it lets us do is it lets us sample inventory life cycles. So we can basically sample a bunch of outcomes, and then we can calculate aggregate statistics. So we can say, hey, based off of what we sampled, what is the average cost? Right? And there's a couple others we might be interested in as well, like the average number of steps from start to finish. But the big one is cost. Now, one thing that you might be interested in is looking at the statistics for a specific outcome, right? So specifically for items that end up being donated, what is the average cost, right? One way to do this would be with rejection sampling. You just sample a bunch of them, only look at the ones that end up being donated, not super efficient. Another approach is to reverse the direction of the graph, and then we can start our random walks at the state of interest. So we can simply start walking backwards from the donated state, right? And those final outcomes now we can start in states. This also allows us to unify the cost model with the propensity model, because you can take the output of the propensity model as a distribution for these starting states now. So for example, if you see that's, you know, it ends up being sold and then returned 95% of the time, then you can start and unreturned 95% of the time. It'll give you a general sense of what the cost of that is. Right. And ultimately what this lets you do, it lets you sort of assign financial impact to these waste outcomes, and you can use that to direct you know, business action.
Before we end, I would like to spend a moment reflecting on the project as a team. This project has used the past 2 years of training and apply that on a real world project for data sets, but a real one and at a large scale. We would like to thank Amazon Global Sustainability for trusting us with a project that matters to them. To Hugo and Dennis, the conversations that we have really challenge us to not only think critically about problems, but also how to communicate that to business stakeholder. These are the lessons that will stay with us way past this project. To Dr. Ezudine, thanks for all of the feedback on our deliverables for holding us at a very high standard. To Dr. Naliple and the CMU's faculties for making this project possible, and to the project centers for providing us with the support we need. Thank you, everyone. It was a lot of work, but it was worth it. We're happy to take any questions.
The title of the presentation is about the economic impact of product disposal. After you get propensity score, so it's 1 over propensity score, you will get the estimate of impact. But I didn't see the estimate of impact. Did you do that?
Yeah, so what the propensity model gives us is it'll give us the distribution over time outcome. So 95% unreturned sale, 2% donation, whatever, probably, right? So then the cost of waste model, right, with the reversed version, you can then, you know, get the costs, and there's different dimensions to the costs, right? There's opportunity costs, storage costs, transportation, labor, all these things. But you can get the expected cost for these, you know, specific outcomes, right? And then you essentially can do a weighted average based off the propensity. So if sales the most common outcome, then it'll have the most weight in, you know, calculating that general cost.
We also didn't have data regarding costs and actual values for the last piece, that random walk piece that we mentioned. So that we built a pipeline, but we don't have any results because we were not provided the data for that.
If someone has like a 10-second question, we can ask it. Okay, let's thank our speakers one more time. Okay, the last talk of this session will be from our second to Amazon team, so let's give them a little.
Hello everyone, my name is Richa and on behalf of my team, Nidhi, Rishabh and Venkat, I welcome you all to our capstone presentation. Our project is titled The Climate Pledge Recruitment Propensity, sponsored by Amazon Sustainability, and over the next 15 minutes, we're going to walk you through what that means, why it matters, and what we've built. To set the stage, let me briefly introduce the Climate Pledge. In 2019, Amazon and Global Optimism started Climate Pledge as a commitment to reach net zero carbon emissions by the year 2040, a full decade ahead of the Paris Agreement. Since then, the initiative has grown on to include more than 650 companies worldwide, spanning virtually every major industry. The goal is straightforward: bring together the world's largest companies, align them around a shared climate commitment, and accelerate global decarbonization at a scale that no single organization could achieve alone. There are tens of thousands of companies from around the world that will join this initiative. Each one of them has a different emissions profile, different sustainability commitments, and different likelihood of joining. So reviewing all of them practically is impossible, and without a structured approach, it's hard to know where to focus first. What we need is a data-driven way to identify the most impactful companies to bring on board and why. To address this challenge, we built a three-step output model. Our first model is the propensity model. It is a machine learning model that calculates the propensity that any given company will join the Climate Pledge. Second is the impact score. We combine the propensity score with companies' reported emissions, calculate the potential impact of recruiting them. Next, we have the prioritized targets list. The top 100 companies emerging from our combined analysis are segmented into three categories. High propensity and high impact are the immediate priorities. High propensity but moderate impact are the quick wins, and low propensity but high impact are the strategic long-term targets. Our model draws from three different categories of data. First is the emissions data, which is Scope 1, Scope 2, Scope 3 emissions along with carbon intensity metrics. Second is the sustainability initiatives. Participation in programs like the Science Based Targets Initiatives, EV100 and RE100 memberships, and carbon disclosure projects, project disclosures to signal how serious the company already is about their climate action. Third is the firmographic data, which includes the revenue, employee count, sector, and region. This helps us compare companies on an equal footing across industries and geographies. While ultimately the dataset was helpful in providing us information needed for our analysis, there were some challenges that we came across. First, corporate emissions data is fragmented. Each company reports it in a different format, at different frequencies, and using different units. We started by collecting publicly available company reports and then converted them from PDF to text and used a large language model to extract the relevant emissions figures. We then standardized units and reporting years and worked out to match companies between different data sources to build one unified dataset.
Let's talk about how we build propensity models. So if we think of generating propensity score, the natural instinct would be frame it as a binary classification problem. The companies who have joined the pledge label them as 1, and the companies who haven't joined the pledge yet label them as 0, train the model, and generate the propensity score. But there is a fundamental flaw with this logic. What it actually means if we treat non-signatories as 0. We are basically telling the model that these are the companies that will never join the pledge, which is not necessarily true, because many of these companies may join in the future. So when the model runs on incorrect training label, it builds the distorted picture of what the actual joiner will look like, and the score generated by the model will be unreliable. That was the core problem which led us to try a fundamentally different approach.
So the solution is PU bagging, which is positive unlabeled bagging approach. Instead of fitting every company into 0 or 1 box, we will work on the fact that we know for sure. That is, the company who have joined the pledge, label them as 1. But the companies who haven't joined pledge yet, we will mark them as unlabeled rather than confirm negative. So how this approach works? First, we will divide all the unlabeled company into different group called bags. Then we will build a model using non-TCP signatories as confirm positive along with 1 bag of unlabeled companies as provisional negative. Then we will repeat this process across multiple bags and we will build multiple models which is trained on slightly different data. And finally, we will average the prediction from all the models to get the final propensity score. So the advantage of this approach that it doesn't penalize the company who haven't joined the pledge yet, but it will learn from its characteristic and try to build a picture of what the actual joiner will look like. Of course, a model would only be useful if we can demonstrate that it actually works. So how we would validate this? Since we do not have the ground truth labels of the companies who haven't joined the pledge yet, we designed a validation framework on the basis of what we know. So we started with the non-TCP signatories and we randomly picked 56 of those companies and marked them as unlabeled. Then we trained our model on remaining data and generate propensity score and asked, did model recover those hidden signatories? If those signatories got a higher propensity score, even the model has not seen them. So on hidden recovery test, PU bagging was able to recover 34 out of 56 hidden TCP signatories, while standard XGBoost was able to recover only 26. More interestingly, PU bagging also identified 13 high new propensity prospect, which XGBoost completely missed. If we look at the propensity score distribution generated by the standard XGBoost and our proposed PU bagging approach, with XGBoost, 90% of the companies scored lower, falling into the lower propensity bucket, scoring between 0 and 20, while with the PU bagging, the scores are generated are much more wider spread. So many of the companies are there in mid to high range bucket, which gives recruitment team some tier to work with, while with XGBoost, all the population looks the same.
We also examine factors that greatly influence a company's propensity score. One of the single most contributing factor is reporting completeness. How thoroughly a company discloses its emissions data. CDP disclosure status and participation in initiatives like the Race to Zero also rank highly. This suggests that companies with established mature climate reporting practices are the most natural recruitment prospects. Company size, revenue, and North American presence also play secondary but meaningful roles.
To generate the final list of priority prospects, we have built a composite score, which is based on 2 signals. The first one is propensity percentile, where a company is ranked based relative to all others based on likelihood of joining. The second one is the emissions percentile, where a company is ranked based on total carbon emissions. Both the signals are then converted to a 0 to 1 scale and multiplied together. This ensures that the composite score balances both dimensions.
On the basis of composite score, we identified top 200 priority prospects, which we divided into 3 actionable groups. So if we look at the chart on the x-axis is the likelihood of joining, which is their propensity scores, and on y-axis is their total carbon emissions. So if you look at the right to top quadrant, there are 50 immediate priority prospects whose likelihood of joining is high, as well as their carbon emission impact is huge. Quick wins are the 20 prospects whose likelihood of joining is high, but their carbon emission impact is moderate. These are the companies that would accelerate pledge actions. And on the left are the strategic long-term 30 prospects whose likelihood of joining is currently low, but their emission impact is high. These are the companies. Which requires tailored engagement.
Looking at who these 100 companies are by sector, tech and electronics contributes and leads with 34 prospects out of 100, retail and consumer at 20, followed by manufacturing with 16, and transport and logistics with 30. By region, Europe accounts for 54 of top 100 prospects, which reflects the strong regulatory environment and disclosure culture in that market. North America contributes with 36 and Asia Pacific with 11. That concentration in tech and electronics helps in the concentration in tech and electronics shows us what the regulations and sustainability report and disclosure culture are there in tech and electronic companies.
Now moving forward to the limitations and future scope. First, the companies lacked emissions data, which affected our model performance. Second, we lacked historical emissions data to analyze changes in emissions over time. Third, our model lacked a greenwashing signal, meaning companies could score well based on their actions even if they do not follow their commitments. Looking ahead, there are two key areas of improvement. First, we could incorporate peer effects to fully capture the influence of industry competitors on climate commitments. In addition, we can also introduce sector-specific ways to improve accuracy.
Together, we have evaluated more than 4,000 companies worldwide. In a pool of 4,000 companies, we have identified top 100 prioritized prospects, which have been getting from most impactful companies and high likelihood to join. Together, these top 100 prioritized prospects give us 58.1 billion tons of carbon combined if they are recruited. Together, this is the potential impact of the data-driven analysis.
We would like to extend our sincere gratitude to our sponsoring presentator, Ben Jasop, and faculty advisor and capstone coordinator, Dr. Yana Miltige, for their constant support and collaboration throughout the project. Thank you everyone for listening, and we're happy.
Okay, questions? Okay, so I have one question for you. In your feature importance spot, you showed a number of different features, and I was curious why you think some of those might have been so impactful. The feature importance spot before. So, for example, North America shows up as a particularly important feature. Could you explain what that might mean for recruiting, either specifically targeting North America or staying away from North America? What might that mean?
To be honest, when we were working on the project, we thought maybe North America would be one of the top regions to come across because of how tech is concentrated in the region. But Europe came across as the region with the most prospects, and I think that is because of how laws are in Europe with the disclosure practices and sustainability reports. So companies there have been publishing sustainability reports at regular intervals. So that is what makes the reporting closeness a very good factor for the propensities.
Other questions? Okay, I have one more question for you guys. If you wanted to incorporate those peer effects, I do think that would be a really interesting prospect. You can imagine if you're the lone company that is the only one in specifically, wearable electronics, who's not in the climate pledge, that might make you more likely to do that. Can you talk a little bit about how you would see incorporating that from your data perspective and into your models?
I'm understanding the question, right? We can see when the first company from a particular sector or region is joining such initiatives, and over a period of time, you could track that particular sector and region and see at what frequency the other companies surrounding that sector or region join in these initiatives and progress and track their progress with respect to their emissions. And that could be how we could see how the peer effects, if they actually make a difference in such kind.
Cool. Any other questions? Okay.
So I want to ask about the data. So I see one value in Latin America. So is your data imbalanced? Like why do you have just one recommendation there from Latin America and 11 from Asia? So what's happening?
Yeah, so like when we started gathering the data, there were like more regions, so companies were like publicly publishing the data, while some of the regions like where we find that the company were not disclosing their data publicly. So there is a data imbalance which is leading to that result. But if we get that data, then might we get different results. But because of the data limitation, we get this result.
Okay, if there's no other questions, let's thank our speakers one last time. Okay, so that's all of the talks for Project Day completed. If you are in the graduating cohort, we're gonna go up and take a photo. So text your friends and make sure that they can come back to the room before we go outside and enjoy the poster session. So please, all of our audience participants, feel free to go and potentially snap some pictures outside or